Hello. Sorry for bad quality of video, but I cannot fix it right now. So let's just write a contest. I hope in like 3 hours it will become normal. Let's see the problems. Greedy greed. Top left to the right. Right or downward, always moving to the greater value, or to the greater value. The value of the path is the sum of the values. Does there exist an m by m grid of non-negative integers such that no greedy path achieves the maximum value among all down-right paths? I think if it has 1 or it is 2 by 2, then no. Otherwise, yes. So if n equals 1 or n equals 1 or n equals 2 and m equals 2, return true, else return false. Let's see. No, yes. Yes, no. So let me think. What if it is... So if it is 2 by 2, then it's easy. What if it is 3 by 2? Does there exist such a grid? So this doesn't matter, this doesn't matter. So we can take maximum of these two numbers. We can always take maximum of these two numbers. But if we go here, we definitely skip this number, which can be infinite. Right? So I guess that's correct answer. I just wanted to be certain. Okay, problem B, pile shuffling. We're given n binary piles, the ith of which consists of ai zeros on top and bi ones at the bottom. In one operation, we can take the top element of any pile and move it to any position in any pile, including the pile it was taken from. Calculate the minimum number of operations required to make it so that the ith pile consists of ci zeros on top and di zeros or di ones on the bottom. It's very easy, isn't it? only top element. It's interesting. What if we can take any element, then the problem is very easy. But what if we can only take the top element? Okay, let's take all piles where we have not enough, where we have too many ones. There we need to remove all zeros and then remove all some ones. After that, I think I understand. So AI, BI, CIDI. Okay. I think we might need long. Okay, so let's go through the arrays. Okay, so first of all, zeros. Zeros. So if let's also have the answer. So if BI is greater than DI, then we will have to remove all zeros and all ones. So let's write it like this. It's hard. It's hard. It's not that easy. Okay, so first of all, there are several piles where the number of ones, so where B is less or equal than D. There, we just work with zeros. It's quite easy. Also, there are some piles where A is less or equal than C, and there are some piles where A is greater than C. So these are very easy. We just put here some zeros if we need. Here, we need to remove some zeros. We need to remove some zeros and put them here, for example. And finally, there are several piles where B is greater than D. And the first thing we need to do is remove all zeros from them. Then we need to remove some ones, and then we can put zeros back. So all these zeros should be put here. So let's calculate the length. So first of all, we remove all these zeros. We don't remove all these zeros, I think. For example, we can remove some zeros, then remove all these ones, and then put here the zeros. So there won't be any extra operations, which we didn't want to do. So this can be done in the end. This is done in the end. This doesn't matter much. But this should be done in the beginning. And we... Gosh. So we remove D zeros. No. We remove... I'd like to formulate this in terms of extra operations. So which operations we didn't want to do? Basically, we remove some of the zeros, put them here, and then put some of these zeros here. So we need to make A operations, and then make C operations. The problem is the order. So for example, let's say that here we have some capacity Q. Then we want A to be less than Q or equal. Then we want then we have some next column, which is A prime. And we want A prime minus A also be mostly Q. No. A prime should be at most Q, right? A prime minus C should be at most Q. So A should be at most Q, and A prime minus C should be at most Q. And in the second case, we want A prime to be at most Q and A minus C be at most Q. Is it true that we just sort by A? But then we will have A at most Q, A prime minus C at most Q, and A prime prime minus C prime at most Q. Do we want to swap these two and have A prime prime minus C and A prime minus C prime prime? So if A prime prime is greater, then of course we want this. So we just sort by increasing size of A prime. Maybe. Okay, let's start with easy ones. So if bi is at most di, then answer plus equals maximum of AI minus Ci and 0. So this is easy. This is this pile, and it is dealt with in the end. Else, we have these piles, right? So first of all, we will have to add to the answer b minus d. Yes, but also we have to deal with these AIs and CIs. I guess let's make VPII AC, and we put here the pair AI CI. And also I'm interested in these ones. Okay, so let's do it with an if. So if AI is at most CI, if AI is at most CI, then Q plus equals CI minus AI. Else answer plus equals AI minus CI. Yes. Okay, in the end, let's calculate how many extra operations we did, right? Let's calculate how many extra operations we did. Okay, let's go. So first of all, we need to sort AC. Then we go through this array. So what do we do? First of all, we need to put all okay, let's just do it. So we say that we remove all A's into Q. So we try to. So first of all, answer plus equals A. This is definitely true. And we also remove A from Q. So if Q is now negative, then we don't have any place. So if Q is less than 0, then answer plus equals minus equals Q, and Q equals 0. Now Q plus equals C, and we continue. Okay, let's see. 230. 330. So here it says that my answer is incorrect. Let's try and see. So one. This is the example that we see here. So what? The first pile was 1, 3, but needs to become 1, 2. So in it, I don't know what to sort by. I'm not sure about what to sort by. So zeros are equal. So actually that means that... here we have too many ones. What? We put 0 here? We can put 0 in the right position. We can put 0 in the right position. That is gorgeous. So we can always put 0 in the right position. We don't need any extra operations. I was wrong. I was wrong. So basically... So what's happening? So basically... Again, so this is easy. This is just removing these zeros. But here, we can put these zeros in the right positions here. So the only problem is that we need to remove all zeros and all extra ones. So that's the problem. So we don't need any sorting, actually. We just need to add AI to the table. That's the thing. 230, right? Yes. It took too much time, but I'm glad we solved that. Problem C, Manhattan pairs. We're given n points on a 2D plane. Select n over 2 disjoint pairs AIGI. Two disjoint pairs. Divide points in pairs to maximize the sum of Manhattan distances between points in pairs. A nice one. Nice one. So we have some points. And we need to maximize such sums. So if we have just one D array, then we just take the leftmost and the rightmost. Always. The problem here is that it doesn't work. Can we just do it greedily? So can we just take always a diameter in this graph? I don't know. So I think we always either take the farthest points like this, or the farthest points like this. So either with the minimum and the maximum sum of coordinates, or the minimum and the maximum difference of coordinates. However, what if some point is both maximum sum and maximum difference, for example? for example, the top point looks like this. Nothing here, nothing here. And we take minimum sum and minimum difference. For example, here we can do like this. And here we can do like this. Usual way to solve such problems is rotate it 45 degrees. So let's rotate. What now the distance is? The distance is now Chebyshev distance, where between 2 points we just take the biggest of these 2 coordinates, I think. Yeah, we just take the biggest of these 2 coordinates. Okay, so we have several points. We can take 2 of them and get the maximum of this segment and this segment. Is it true that we just always take it greedily? So if we took some long segment and another one should have been like this. So this is the first place, this is the second place. Could it make sense to instead take... So if they don't intersect, so if this is longer, then we couldn't have taken it. We should have taken the vertical. So this is shorter. And if it is shorter, but still, this could be bigger. This could be bigger. And also we have something like this. For example, diagonal segments. So we could have taken this one and this one. Why isn't it bigger? Crazy problem. How do you solve such a problem? Okay, I think I will do it later. I think that this problem will be perfectly solvable by ChatGPT, and that's why I think I will be defeated by this in this problem by a lot of people. A lot of people. Not in my friends list, maybe, but oh, it's crazy. It's crazy how slow I am. This is just ridiculous. I think we already need to solve the hardest problems because I suck at the easier ones. Let's just have a look. Take a look. Oh my god, I will need a fast FFT. Okay, never mind. We're given a tree with n vertices rooted at 1. For each I, a car will enter the root at time li. It will then instantaneously travel from the root to vertex I through the unique symbol path and park there. It will leave through the same path in the other direction time array. During the time when the car is parked in the vertex, it blocks other cars from traveling through that vertex. The tree is called valid if and only if all cars are able to enter and leave the tree at their desired times. Count the number of pairs of sequences LR such that Li is less than Ri. Their concatenation is a permutation of 1 to 2n and the tree is valid. Calculate the sum of the answers to the problem over all labeled trees with n vertices and k leaves. The root does not consider the leaf. Since the answer may be large, calculate modular number. Okay, let's have a look. Let's have a look. So we sum over all labeled trees. Of the number of pairs of sequences LR. We can do it in the opposite way and start with the permutation and then count the labeled trees. So let's start with permutation. Or I don't know. So we just want to calculate the number of both trees times the permutations, right? So let's say that we have a polynomial that says okay, so let's just think about the following thing. We have this, and we just put 1 and here and here. So first of all, 1 should be the last one to be introduced. Or no. No, 1 can be not the last one to be introduced. What really is true about 1 is that L1 equals R1 minus 1. So we add 1 and we immediately remove it. That's the only restriction. That's the only restriction. We need to put 1 and then immediately remove it. So that's the only thing. So there are 2n minus 1 choices of where to put this L1 and R1 in our permutation of size 2n. There are 2n-1 ways to do it. So we put it and we remove it. After that, that is simply a problem about two independent trees. Sorry. It's a problem about two independent trees. That is a problem about two independent trees. And since it is, we can somehow combine them. So how do we combine them? We combine them by saying that, so we have some tree A1 with B1 leaves, and 1 vertices and K1 leaves, and 2 vertices and K2 leaves, etc. and U vertices and KU leaves. How do we, let's define the order. So this is the tree where 2 lies. This is the tree where the minimum of these numbers lie. The next tree is where the minimum of all these trees lie, and etc. Okay, so we defined it this way. If we do it, then how many ways to combine them? So first of all, we need to choose the numbers of vertices. How do we choose the numbers of vertices? Basically, there are n-1 numbers, and we need to choose any subset So n-1, choose n1. Then we say that this is two is not necessarily the root. Actually, 2 is not necessarily the root. This is actually crazy. So I don't want to count the order twice. I think I think we can assume that we only choose the subset, and the tree does the work on making the right permutation itself. So we just need to take the subset, I think. Yeah. Okay, here we choose. So we have n-1 positions, but we have already removed some subset of size n1. We definitely have also the number which is minimum number here. n1 minus 1, I think. Okay, so n2 minus 1 then. Then n minus 3 minus n1 minus n2 over n2 minus over n3 minus 1. And so on. So this product. Okay, let's rewrite it. So it's n minus 1 factorial over n1 minus 1 factorial and n minus n1 factorial times n minus n1 minus 2 factorial divided by n2 minus 1 factorial and n minus n1 minus n2 minus 1 factorial. Okay, then n minus n1 minus n2 minus 3 factorial over n 3 minus 1 factorial times n minus n1 minus n2 minus n3 minus 2 factorial, and so on. In the end, we will have n minus u minus all n's factorial over nu minus 1 factorial times no, I'm not right. I'm not right. It should be minus 1, right? So we have n minus 1 vertices. N minus 2, I think. N minus 2. Oh, it is always a 2 here. I think it is always 2 here, because each time we have n minus 1 vertices, we removed some n1, n2, and 3, maybe something else, and then minus 1 because we already know one of the numbers. Okay. So it is always a 2. So it is always a 2 here. 2, 2, 2. Good. So what do we have in the denominator? Basically, we always have minus 1. Minus 1, minus 1, minus 1, etc. So in the numerators, we always have minus 2. In the denominator, we always have minus 1. Okay, this is basically 0, right? This is basically 0 because n is sum of all n, little n's plus 1. So this is 0. Okay, let's go then. Okay, so this divided by this, let's just write something we can write. So n minus 2 factorial. So here we simply have n1 minus 1 factorial. Here we have n minus n1 minus 1. Then here we have n minus n1 minus n2. But why? It depends on the order. Why does it depend on the order? Because it should depend on the order. Yes, it probably should depend on the order. What if I don't want it to depend on the order? Okay, let's put it this way. So I want to count the number of forests, to calculate the number of forests of size, for example, n. Actually, it is n minus 1, but I don't care. N. With exactly k leaves. So this is called, I don't know, forests of nk. So we know that forests of nk is exactly equal to what? So it is equal to trees of size n plus 1k, but only if and divided by 2n minus 1, but only if n is equal to n is at least 1, so that the root is not a leaf. If the root is the only vertex of the tree, then I consider it a leaf. So if n is exactly 1, then if n is 0, also plus 1. So if n is 0, then I would say that it is equal to t of n plus 1 and k plus 1, because it is a leaf. Okay, something like this. Good. Very good. And now we want to ask ourselves, what is the f of n and k? What do we know about this thing? And I claim that we need to iterate over all possible first trees. So we iterate over all possible first trees. So let's say that it is sum for all n1s from... So let's say that n is at least 1 and k is at least 1. Otherwise it doesn't make sense. So let's start with f0, 0 is 1. f0 and anything is 0. And f of anything and 0 is 0, which is greater than 0. So this is known. So let's now assume that f of n and k, where they both are at least 1. Then we take the first tree, which contains the minimum index. Then we start from 1 to n, and we go here for k1 from 1 to n. What do we want then? First of all, we take t and 1 k1. So we take a tree. Okay, let's also say that it is not necessary to have 1 in the root. So in all our considerations, it is not necessary for 1 to be in the root. So in the end we will divide by n, I guess. But 1 is not necessary at the root. So we also need to choose the root. So we consider the rooted tree and we choose the root. Okay, then we just need to take all trees. Then we need to take any subset of vertices from 1 to n which contains 1. it is choose of n minus 1 and 1 minus 1. Because we know that 1 is inside this set. Then we map them one on the other, right? Do we just map them in the increasing order? I think yes, we just map them in the increasing order. Yes, and we can do that. If we map them in the increasing order, and then, what then? Then, when we have mapped it, we say that we also need to shuffle the permutation. We also need to, so we have a permutation of size 2n, and we want to choose any n1 elements, but this is easier, so we just add 2n over 2n minus 2n1. So that's really easy. We just do that. Okay, and then after we've done this choice, we also need to take forest of n minus n1, k minus k1. So on the remaining vertices, we also need to make a forest. Yeah, that makes sense. That makes sense. So now let's say that it is... Now let's say that we want to look at sum of xi, yj, f, ij divided by, I think, I factorial and j factorial, something like this. So let's look at this thing. Do we want to look at this thing? No, we want to look at this divided by n factorial and divided by 2i factorial and 2i factorial. So we divide by these two things. Good? Do we just divide by I factorial and 2i factorial? Okay, let's just do it. So first of all, let's just divide f by it. So let's see what we see here. Now it is f and t. So it is sum t n1 k1. So first of all, this thing is divided by n minus 1 factorial. So we are left with 1nth. Okay, here we have division by n1 minus 1, but we multiply by n1 factorial. So we have n1. And also we have n minus n1 here, and it is divided here. Okay, we forget about that. Now we also divide by 2i factorial. So we just divide here, and multiply here. So that's it. So this is the formula. So f n minus n1, k minus k1. Excellent. This is just excellent. So this is our formula. This is our formula. How now let's say that let's fix n, for example, n. Let's say that we have f n equals sum f n k of y to the power k. Let's look at this thing. Then basically we see that f n is just sum from 1 to n t n times n1 t n1 times f n minus n1, I think, right? Yes, I think so. I think so. Now let's also say that f is sum of f is simply sum of f n k y to the k x to the nth power. What can we say then? Then we can say that f n is not n. We can say that f x to the n is sum of t in x to n1 times n1 over n times f x n minus n1. What can we say? I think we can say that there are some derivatives. So what I want to say? Okay, first of all, let's put n here and remove it from here. So how to get this thing? How to get sum of n1 times x to the power n1? To do that, I think I need to take derivative of t by x and then multiply by x. So now I also simply multiply by f and I get derivative of f multiplied by x. now we want, let's say what is t in terms of f. So how to find the number of trees if we know the number of forests? So if we want to find the number of trees, first, for now, let's forget about what? No, let's not forget. Let's not forget. So f t of x to the n is what? Okay, and yk. How many trees are there? First of all, we need to choose which vertex will be in the root. And there are n ways to do that. Then we need to choose in 2n ways, 2n minus 1 ways, where it is exactly in the tree. Then we need to we need to find where it is exactly in the tree. And when we need to choose any forest. Forest with one less vertices and one less leaves if n equals 1. Okay? So why do we even do that? We even do that because we want to say that f00 is not 0. I think that comes down to writing here like f plus 1. So let's just say that we put f y k x n minus 1 plus 1, which means that when x equals times x, I think, which means that when n equals 1 and k equals y, I think. Okay, that makes negative sense, but let's go on. Okay, so we have f with n minus 1 vertices. Let's multiply it by x. Then let's take a derivative. We always take derivative only by n. So we multiply it by x and take the derivative. No, we take f plus multiply by x, add yx, but it is not the end. So now we wanted to multiply by n. How to multiply every coefficient by n? We need to take a derivative and multiply by x. That's not the end. Now we also need to multiply by 2n minus 1. How to multiply by 2n minus 1? We need to multiply by 2n and then subtract 1. Let's do that. So first of all, let's multiply by 2n. For that, we need to multiply by 2 and then multiply by n. And then we need to subtract 1. And for that, we need to take fx plus yx prime x. So this is what we need. Okay, let's go. So it is x times what? 2 some derivatives. So let's take the derivative of this thing. This is y plus f prime x. And we need to take the derivative. We need to take times x and take the derivative of that. And then subtract f prime x and y. Так. It is not lovely. It is very not lovely. Okay, it is x times what? 2y plus 2f plus 2f prime x. This is removing this x. And then we need to take the derivative of the left thing. So let's take the derivative of the left thing. The derivative of y is 0, so skip that. 2f prime x and plus 2f prime x again and plus 2f prime x squared. And then minus f and minus f prime x minus y. So in the end, it results in something dubious. Y plus f plus 3 plus 5 x f prime x and plus 2 f prime x squared. I guess that is very bad. I guess that is really, really bad. But okay, whatever. And now we say that we also know this equation. So let's write it. So f prime, yes, it's just f prime. F prime x equals to x times t prime times f. F times t prime. T prime fx. So we know that f prime is f times t prime. Good. And we know that t We also need to take t prime. Oh my god. I hate it so much. Also, why is it two variables? I don't see here any reason to have two variables. Why isn't it just one variable? It is not one variable because we have this thing. Okay, the easiest thing I could think of is say that f prime over f is t prime, then say that it is logarithm of f prime equals t prime, right? And this means that logarithm of f equals t, which means that t is e to the power f times some polynomial of y. Okay, and now we need to find exact polynomial by solving this differential equation. So let's solve the differential equation in terms of f, I think. Although I would like to solve it in terms of t, but it seems like a mess because f is e to the power t times some function. So let's call this function, I don't know, r, and r is some function of y. The saddest part is that most probably I made a mistake somewhere. But okay, I think when we find this mistake it will be easier. So let's say that we want to look at no, it shouldn't be bad. It shouldn't be bad. I believe it shouldn't be bad. So t, this is equal to t, right? T is just this thing. Yes, t is just this thing. So we know about the t, that t is equal to x times y plus etr plus how to take derivative of this thing. This is very hard. Differential equation. It has two primes inside, which is not good. Can I just write that it is log f? Can I just write that this is log f? This is crazy. Let's try. So log y is x times a plus y plus 5xy prime plus 2x squared y prime prime. Can we solve that? I guess we cannot. Let's put here 4, for example. Can I solve it when a is equal to 4? It doesn't want to do it, right? So much time in trash bin. Ah, of course Turi solved it. It is so... It's such an easy problem. What? They already did it? Okay, maybe I'm missing something here. Maybe I'm just missing something here, but... Finally, actually we don't have any sorts of. So now I can say that yk is const. Can I do it? Can I say that now yk? I cannot. This thing is killer because can it be solved with Newton method or something like this? Well, we can take a derivative and say that f over f prime over f is equal to some sort of garbage. We can. Okay, let's say that f over f prime over f is some sort of garbage. Which sort of garbage, actually? F prime over f is the derivative of this thing by x, which is y plus f plus 5x f prime plus 2x squared f prime prime plus x f prime plus 5x squared f prime prime plus 2x cubed f prime prime prime, which results in y plus f plus 6x f prime plus 7x squared f prime prime plus 2x cubed f prime prime prime. And in the end we can say that f prime is f times this garbage. What can I do with it? I don't know, because like what can I do if it is two-dimensional power series? It's two-dimensional. Okay, if we let's assume that we have one here, then everything is easy. Everything is really easy. However, if I multiply it by, if I add y here, it is actually becoming not very easy, and it is becoming a piece of garbage, because now everything is some obscure polynomials of y. Can I just write here 2, for example? No, I cannot. I know what I can do. I think, okay, let's multiply everything by y. So let's say that yf prime is yf times, no, let's divide everything by y. Let's divide everything by, shit. First of all, f. Okay, I can say that. Let's say that. Let's try and say that f is equal to 1 plus yg. Let's try and write like this, I think. Then we have yg prime equals 1 plus yg times okay, I have a problem here. The problem is nothing is divisible by y. Left thing is divisible by y, but the right one is not divisible by y. And I don't understand why. Okay, let's look at it in terms of divisibility by y. Okay, maybe this one we can figure out. Ah, t is divisible. Of course, t is divisible by y, because a tree with 0 vertices is a nonsense. So it is yg. That's it. Okay, so we have y. No, it's very strange. Okay, yg prime is yg times y plus yg plus 6f x yf prime plus 7x squared yf prime prime g plus 2x cubed y g prime prime prime. And we can divide by y squared. So we know that j prime over y is equal to g times 1 plus g plus 6x g prime plus 7x squared g prime prime plus 2x cubed g prime prime prime. So this is now some differential equation. but with this strange y. I hate that. Why did I end up in this trap? Why did I end up in this trap? Okay, so what can we do? What we can actually do? We can try several y's. Like what? Why? No, we cannot do that. Okay, we can try several y's. It will be several differential equations with different y's. And then we can solve them and we can get several polynomials. For each y, it will be a different polynomial. And then we can say that we are only interested in the coefficient near x to the nth power. And here we have some numbers. Oh shit, we can do that still. It is like a matrix multiplication? No, it is not something good. It's not something good. No. Or is it? No, it is not something good. It is something very bad. I don't know what to do here. It is some two-dimensional power series. How the hell can I find some its coefficient? So I have a Newton exponentiation here. It is ready. And it would be ready if I knew that y is equal to 0. Or if y did not matter, for example. If y could be constant. But y is not a constant. Y is a huge number. And I am even ignoring the fact that if this is most probably incorrect power series and differential equation. Most probably it's not correct. I need to think a little bit more, and then I think we give up on this problem. Unfortunately, we need to give up. And that's because I'm so slow. Okay, I know I want to find the coefficient y to the power k. Then I want here in g. Then I want the coefficient near y to power k minus 1 here. That means I want power y to k minus 1. Ah, no. Yeah, actually, what if I take a constant y? Not a constant y, but a constant term. Unfortunately, it doesn't work, yeah, because we will have a problem here. This problem is like the worst. It's like the worst. How did that happen? How did that happen? Okay, I guess we just look into other problems. Yeah, very bad because we only have 34 minutes and I still didn't even solve problem C. Which problem did people solve? Of course, C and D. Oh, that's exceptionally bad. Okay, how to maximize Manhattan distances? Can I just try going from here to here? and going from here to here. So just two answers. Can I just try two answers? I think no, because when I have taken this answer, it is still possible that I need to take this one, right? I'm actually quite sad here with all this situation. Okay, let's just try the first thing that comes into the mind. I don't know. I don't know how to solve this problem. Let's just do a greedy solution because I don't know. Hmm. VPII. VPII. P. Okay, let's look at the smallest and the largest number in SM and in DF. So if, okay, while SM begin second, y I mean, is used, let's just remove it. SM erase SM begin. And same with DF. And same with R begin. Okay, now it is clean. So now if SM R begin X minus SM R begin begin X, what do we do? We say that used SM begin Y is true. Dot. And R begin is also true. And answer I equals SM begin X, SM R begin X. Else same with diff. Minus? Why? 4, 1, 2, 3, 8. Okay, let's just try to submit it. Maybe it's also a correct answer. I don't know. No, it is not. I need to compare it with diffs. What the hell? Why don't I know how to solve such a problem? How can I solve this problem? Okay, it would be easy if there is no such situation. However, unfortunately, there is such situation. So some points are located more in one direction and some of them are in the other. Okay, I think we just need to look at the example. I think the example might simplify everything. Let's see what we have. -1, -1, -1, 2. Oh no. Okay, -1, -1, -1, 2. -2, -2, -2, 0. 0, 2, 2, 3. 0, 2, 2, -3. -4, -4, -4, -2. 0, 1, -4, -2. -4, -2 twice. Yeah, it is twice for some reason. Let me put it like here. And last point was 0, 1 first of all. 0, 1 and -4, -2. Okay, let's make the segments. So it says 8, 1. 8, 1, 2, 3. 9, 10. 7, 5. 2, 3. 6, 4. So these two are the farthest points, but apart from them, these two are the farthest. And it decided to take these two are the farthest, but it's not a good idea to take them. Again, if we rotate it 45 degrees, it's becoming a problem of there are several points and we need to take horizontal and vertical segments and we need to maximize their length. Maybe it was a Kuhn algorithm after all. But no, how can I solve it with Kuhn? Also, I want a maximum width, not the maximum size. I will lose so many duels today, guys. I can solve a 900 rating problem. Okay, let's try to minimize it, for example. What if I want to minimize the sum of Manhattan distances? It is obviously solvable in polynomial time, for example, in cubic time, I think, with Hungarian algorithm. But can I do it faster? Okay, let's rotate 45 degrees and let's take the median. So we have here some median. So this is the median x, and here is the median y. So there are some points here and here, and here we have exactly n over 2 points, and here we have exactly n over 2 points. Maybe just pair up these with this and this with this. Yeah, that's it. Just pair up this with this and this with this. Are you kidding me? Shit. I think that's really it. That's even not funny. Okay. Okay, so we sorted them. What next? Next, I want to divide them into 4 groups. Ah, no. Like this. Dude, like this. Oh my god. Pathetic. This is just pathetic. No, 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 no. This is this is bad. This is real bad. Not a nice thing. Not a nice thing. Oh my god. Okay. Okay, better have. I should have solved that a little bit earlier. Okay, no, no, it's not the worst thing out there, but dude, problem G was harsh. I don't know. Problem G just took all my time and I still did not solve it. Not a good thing. Not exactly a good thing, guys. And it's solvable in 45 minutes. What did I spend my time on? I don't understand how it happened. Oh. I hope you learned something from this screencast, because that was not the best thing I could do in this situation. Thank you for watching.